Okay, the second type of lens is used, a practical application for myopia, where we have nearsighted. This is where the eye is wider and we need a lens to be able to spread the rays out so that they hit the retina properly. And so we get a lens like this where the rays go through and they spread out and then go to the back of the eye. This is where, you know, distance objects are blurry, close objects are clear, or close objects are clear, and we need a concave type lens to be able to, you know, adjust for that there. So yeah, diverging lenses, what happens is the rays come in and then they diverge, and as they do, we have to trace them backwards, and when we trace them backwards, we end up getting a focus that is negative, and that is a critical part of this, maybe the most critical part of this lesson. The focus is negative on the left-hand side, and that is critical there. So yeah, again, the positive side is where the reflected rays go, and this is the second of the two lenses that we're going to be looking at. You do need to remember both names. It's diverging and concave. So concave because it's caved in, right? And then diverging, the rays diverge. All right, let's say we have an object out on the left-hand side here, and we've got a concave lens, and we want to draw the image. So I'm going to walk you through this one, being the first one. Let's go ahead and try this here. So we have the parallel ray, comes, hits, and then the tail should take us to the focus. And so what will happen here is we got the parallel ray, this will go out, and then the tail would take us to the focus. And then the center ray just goes straight through the center. And those are the only two rays we need. We see those rays are diverging, so we trace them backwards. And when we do, we end up getting the image back here. And that's always what happens with a concave lens. You're always going to get something that's virtual. It's always going to be on the negative side. It's always going to be upright, and it's always going to be reduced. And we always get that with a concave lens or diverging lens. So again, focal length is negative. That's a critical part here. DO is positive, even though, again, it's on the left-hand side. DO is always, always, always positive, unless you have a combination lens, which we don't do in our class. And so for both mirrors and lenses, DO is positive. And DI is negative for concave lenses. And so it's always virtual. And magnification will always be less than 1 because it's always going to be reduced with that lens. And HI will be positive. All right, so let's go ahead and try this one. This is M29. We have an object placed from the lens, and we want to draw, calculate, and name. And so, yeah, I'll let you do this one. Go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so here's our parallel ray. We have our center ray, and we can draw those backwards. We should get our image showing up there, virtual, upright, reduced rather. For our distance, we should get negative 6.429, magnification of 0.357 for a height of 5, shrinking down from 14. All right, so we don't forget, let's go ahead and practice convex lens. Focal length is 20. We have a 5 centimeter high object placed 30 centimeters from it. And yeah, we can give this a try. So this is on M30, so go ahead and draw it first, and then you can calculate it and name it. And let's see how we do there. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so we should get, we have our parallel ray through the focus, center ray. Again, we could go through the focus and then come out parallel. And we should get our image out here. Real, inverted, enlarged. DI should come out to be 60 centimeters, magnification of -2, and that will make it -10 centimeters. All right, so on this one, we have a convex lens, focal length of 10 centimeters, and yeah, we can try this one here. And so I'll let you, and this will be on M31. You can draw on this one, calculate and name. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so we have our object. And we've got the parallel ray, then through the focus, center ray, trace them back. And we have our image located on the virtual side. And so it's interesting on this one, right? So it's inside the focus, focal length rather, because again, the focus is here. And yeah, the rays come together. We get a virtual upright enlarged image. For DI, -10 centimeters is the location for the image, magnification of +2, and 4 centimeters tall from 2 centimeters. All right, so let's go ahead and try this one, the concave lens this time, focal length -15. We have a 4 centimeter high object placed 10 centimeters from it. And yeah, we can give this a try. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so here's our object, parallel ray, center ray, trace them back, and our image should show up on the negative side, on the virtual side, and so virtual upright in reduced. For our distance, we should get -6 centimeters and magnification of 0.6 for a height of 2.4 centimeters. All right, so let's try this one here. This is a converging lens, focal length 10 centimeters, objects 4.5 centimeters tall, placed 17 centimeters from the lens, and we want to draw the final height, or draw and then calculate the final height and location of the image. So yeah, go ahead and pause the clip and try this one on M33, and when you're ready to check, you can hit play to continue. All right, so we've got our parallel ray and then focal ray. Can do the center ray as well if we wanted to, straight through. And we should get a distance of the image 24.3, magnification of -1.43, and a height of -6.43 centimeters.